Next, we have Alireza Marandi. He's the assistant professor in electrical engineering and applied physics.
Thank you, Azita, for leading the S2I at Caltech and also putting together the symposium and the opportunity to speak here. I know I'm standing between you and lunch, so I don't want any hangry questions. I'll try to go a little fast. But today, hopefully, I'll tell you a little bit about some of the hardware work that we're doing and how we're combining it with machine intelligence to develop nanophotonic breath analyzers. I brought one of these things, if you remember these, to just remind you of the lessons we learned in the past few years, or maybe not, about how your exhaled breath, if you're sick, can make other people sick. And the fact that exhaled breath contains a lot of molecules and a lot of information about the body state is actually something that has been the center of attention for many centuries. More recently, it is actually established that there is a correlation between what exists in the blood and what exists in the exhaled breath. So one can think of breath analysis as a non-invasive replacement for blood test. But the promise goes way beyond that. So there are lots of studies more recently on how you can use exhaled breath to detect cancer in the very earliest stages. And the reason we know that is because of those animals. And it has been shown for many different types of cancers that it can actually detect the signs in a very early stage much better than any piece of equipment in the medical industry. So it is established that exhaled breath has a lot of information. What is challenging is that we still don't know exactly what carries that information. And what is even harder is that we don't really have devices that can access that information. So that's why there is this demand for having an analyzer that can tell you existence and detection of multiple species of molecules in a gas sample, being the exhaled breath. Coming from the optics background, of course, the best way of doing this is using spectroscopy. Spectroscopy is nothing new. You start with a light bulb, a broadband spectrum, and then you pass it through a sample. And because of the absorption features in the sample, you can detect what is in that sample. So it has been done for many centuries, even quantitatively. What is maybe a little newer is that if you use lasers, you can make spectrometers much, much better in terms of performance. That means in terms of sensitivity, resolution, and also speed. And there are so many approaches in the past decade that have been evolved. And there have been a lot of demonstrations showing that laser spectroscopy is the best way of doing this. So again, I'm coming from the optics background. So then you might ask, why don't we have one of these spectrometers at home? If this is so good, this technique is so old, why can't we access that in our day-to-day life? And I want to give you a little bit of sense of why that is. So one of the reasons is that if you want to do a spectroscopy and molecular sensing, you want to look at the wavelength range, which is typically much longer than the visible wavelength. And that's called mid-infrared. So this graph is showing how spectral signatures of different molecules sit on the spectrum. Y-axis corresponds to the strength of those spectral signatures. And these are called molecular fingerprints. So each of them look like something like this in the spectrum. It looks like a barcode. Each molecule has its own barcode. So if you can detect that with a spectrometer, you can basically tell the traces of gases in a sample. And it's not just useful for breath analysis. It's actually important for many other applications, for instance, agriculture and defense. So if you want to think about what we're competing with, these are really our competitors. So they have already shown that the information exists. And the question is, can we get to the regime with the devices and hardware platforms to do similar detections? When I was in grad school, I'll let you guess how many years ago that was. there were many impressive demonstrations of molecular sensing using laser spectroscopy. One example was in glucose sensing with just the fingertip. And it was shown in that study that the performance of glucose sensing with that system was much better than any existing medical devices, including the standard needle test. There is also a similar study around the same time, a few years ago, on breath analysis and looking at different molecules and traces of different molecules. However, these things are neither small nor cheap. So I have the picture of a part of my lab. So you're looking at about $1 million worth of equipment. And I want to draw your attention to this laser, which is sitting there, which is about a few $100,000. It's not for sale, but there's a reason I'll tell you this. And then I have a few components and devices here. These are also effectively a few $100,000, and there's the rest. So let me break it down and tell you why there are these challenges about this being useful for day-to-day life. In principle, you can have this on your kitchen table if you have enough space and you have enough money. But I don't think that's going to be the mainstream. So one of the biggest challenges is that the comfort zones of well-developed photonics is not in the mid-infrared. So it's typically the detectors, the lasers, and the photonic devices that we have are typically in the short wavelengths. And that's where you don't really have that wealth of information. So that motivates the use of nonlinear optics and one specific function of nonlinear optics, which is wavelength conversion. So you can use nonlinear optics, start from a near-infrared laser, which is well-developed, go to the mid-infrared, access that wealth of information. You can use the same platform and come back to the near-infrared and use the well-established near-infrared detectors. So the way we have been doing this on the tabletop is a device that is called optical parametric oscillator. I'm not going to explain all the details of that. I'm just going to tell you that it's a resonator that has a nonlinear material in it. And this is part of that setup. You can actually buy these optical parametric oscillators commercially for only $300,000. The thing they don't tell you is that you also need a couple of grad students to keep them working. Otherwise, it's going to be really hard to get that performance. But that was the time that I actually started developing interest in these devices. Don't ask me why. So the concept of laser is actually very similar to laser, except that it doesn't depend on a laser gain medium. So the equivalence in the radio frequency is the maser, and nobody is really using masers anymore in integrated electronics for creating a source. So everybody's using a nonlinear circuit, a nonlinear oscillator using transistors or amplifiers to make a given frequency. And the idea behind OPO is very similar. So instead of using a laser gain medium, we actually use the nonlinearity to create an oscillator. The challenges so far has been they're bulky, expensive, and they only work in specific materials. And I tell you this because our beloved silicon is not one of those materials. So you need to actually work with some slightly less popular materials. So in the past few years, we have been developing on-chip optical parametric oscillators using lithium niobate nanophotonics. So this picture is to give you a sense of size, either the OPOs or my finger, depending on your perspective, but we can fit now 20 OPOs on a small chip. And these laser-based sources can actually become universal coherent sources, just similar to electronics, the nonlinear oscillators in electronics. So we have been showing that you can use them as a tunable CW source and cover more than an octave. So this is way beyond what can be achieved in a single laser diode, the cheap lasers that we have access to. We have also shown that you can go into the frequency comb regime, so generate frequency combs of light and also short pulses with them. And you can get the tunability, not only in the mid-infrared, but also go all the way to the visible on a single chip. And more recently, we have also shown that it's not just the tunability, you can actually get a very broadband spectrum coherent out of them. So these are all on the source side. So now we're seeing this change that now you can think about a compact source that can be used for this kind of spectroscopic applications. And this is one of the topics of a startup company from my lab, which started very recently to develop this technology for real-life applications. Okay, I told you about the OPO, which was the few $100,000 piece in that whole thing. But then the question is, what else do we need to get to the spectroscopy and be able to detect those molecules with spectroscopy? So if you actually want to do a spectroscopy, you need to go a lot beyond just having a good tunable source or broadband source. And maybe a third of what you see in this picture is because of the extra overhead that you need, including the data acquisition, making sure that tuning is perfect so that you know exactly where you are in the frequency, and so on and so forth. So one of the questions, which is also very similar to the theme of what Young talked about in the imaging, is do we really need to get a clean spectrum? Do we really need to have such an overhead to get a clean spectrum to get access to the information of the molecular content of a sample? So we have been really interested in thinking about this question hard. And one of the ideas that we have been pursuing is that what if we don't really look at the spectrum, we just put the sample inside this nonlinear system and just look at the response of the nonlinear system to the content of the sample. And start with the near-infrared laser and just detect with the near-infrared detector. So we went back to the same $1 million setup, and we have this set up in the lab. One of my first grad students, who was early in his career, I took him to the lab and we stood next to each other, and we decided to exhale into this machine and looked at the output. So we just looked at the detector output as a function of cavity scan. So if we don't do any exhale and we have the box around the thing, we get such a signal. So when we exhaled into the machine, we get something that looked pretty similar but different from the atmosphere. And then when we zoomed in a little bit, we could see that there were some features. So Robbie, who was the grad student who was with me doing this, he thought that's what grad school is about, and that's what his research is going to be. And you'll see that it doesn't stop there. But this was a good indication that maybe there's actually information hidden in that signal, which is very simple to get. So in principle, we're avoiding all the overhead of making a nice spectrometer, but we might actually get access to the molecular content of our Excel breath. So this is actually not completely unscientific. So we need to think about what are the components that we need to have for such a system to work. So the first thing is that we need to make sure that the spectrum of this device, actually the photons that are in the cavity, they have a spectral overlap with these fingerprints. And even in the on-chip platforms that we have been developing, you can already get into the regime that you start seeing this strong molecular features. And you can even extend that using the same lithium niobate material platform or even other platforms to access the mid-infrared region. So that means that the overlap with the spectral fingerprints is already there. So the first piece is good. Now the question is, do we get sufficient sensitivity? So are those features, are they really sensitive to traces of gases as opposed to a lot of molecules? And this was a question that Ravi looked into in a much more scientific way than just standing next to the setup and exhaling into it. And he started looking into the dynamics of how light forms in those long wavelengths inside this nonlinear resonator, only in a very specific region of operation. So what he showed is that if you operate this resonator in one specific region, you can get about 1,000-fold enhancement in the sensitivity of the response you get out of the nonlinear resonator compared to a linear scheme. So this is basically summarized here. So the blue region is the region that is the fundamental limit of any linear spectroscopy technique. And there's always this trade-off between sensitivity and then the concentration or dynamic range. So you can't really have high sensitivity and high dynamic range. And in the nonlinear operation regime, we showed that you can actually break that limit. You can easily get to the high concentration and you still get a lot of sensitivity. So this is only one example. So there are so many other operation regimes that we don't understand and we're actually interested in understanding. But this was a good sign to tell us there is a reason that the sensitivity could actually be there, even without looking at the spectrum. The other question was, can we actually get a specificity? So can we detect different molecules and the responses could be different for different molecules? Selina Zhu, who was an undergrad student in my lab at the time, she looked at this problem by just looking at the CO2 absorption. So she quantitatively changed the concentration of CO2 in this machine, again, the $1 million machine. And then she showed that you can actually distinguish the features between CO2 and N2O. She's now a grad student. She's actually holding a poster in the poster session. So I invite you to ask all the hard questions from her and not from me. But she will tell you a lot more about the details of how this works and how we're pushing this into the integrated photonics. So I told you about the OPOs. I told you about the overhead in electronics and data acquisition that we are going to eliminate. The system that I showed you still uses one of those mode-locked lasers, and those are about a few $100,000. And we recently have shown that you can actually bring that kind of operation of mode-locked lasers to the on-chip platform, the same on-chip platform, which is lithium niobate. And it actually appeared on the cover of Science, so we didn't design that illustration. They sent us that illustration before it was published a few weeks before. And we looked at it and we thought it was just a sketch. So we thought they're actually going to do a lot of artwork on that before it gets published. And they didn't. But the key thing about this image is that it makes you feel that somebody's pressing this chip and it's generating these ultra short pulses. And that's exactly how a mode-locked laser works, except that you need to do it with 10 gigahertz. And that's how we actually make the mode-locked laser with these electro-optic modulators on the chip. The performance of this laser is still not the same as the $200,000 laser system, but it is sufficient to drive the OPOs that I showed you on chip. So with that, I think we have a good path to create the hardware platform. Now the question is, can we actually get that messy signal and extract the information about the molecular content? And that's the idea that we're pursuing with ANIMA. And the idea is that we don't want to understand how this nonlinear system works. Let's train ChatGPT to learn how this thing actually works and then tell us what kind of molecule would be the result of the scrambled data out of the system. So, of course, the exercise is driven by the application, but it could also help us understand a lot of interesting physics about the operation of this device, and that's why we are overly excited about it. It's a good combination of understanding device operation and also moving towards an application. So with that, I should just show you the people who actually did the work. I have highlighted the name of the grad students and the former members of my group who actually contributed to the results that I talked about. I mentioned Selina is going to be out there, so hold all your hard questions, ask all the easy questions, and with that, I'll stop here and thank you for your attention.
Thank you, Alireza. We have time for a couple of questions, so go ahead. Anybody? Oh, go ahead.
Yeah, hello, thanks for the talk. You may have mentioned it somewhere in the site, but I didn't pick it up. Can the spectral analysis also be used in the environment of tissue and liquids, or is it limited to fluids in the gaseous form?
No, that's a great question. I think the remote sensing is something that we have been thinking about, but it's going to be a little different from throwing the tissue or liquid on the device. So the good thing about the gas is that you can kind of protect it from being degraded by all the material degradation. So you can have gases on the photonic system. If you want to go to tissue, it's going to be a little slightly different idea, but the concept should hold.
Because I know several approaches at Medtronic where we tried
Yeah, I think one of the motivations to go to on-chip is to be able to make it small enough that it can also send it to places, including using catheter. But that's probably a few steps away from where we are with the gas sensing. So we think gas sensing is simpler in terms of all the constraints of the devices.
Thank you.
Go ahead.
Thank you. So my question is that you mentioned you want to design a system which can be used as a home device. So for that GPT part, are you planning to just extract what the system is basically doing, or that part will also be implemented on chip? Because like these GPTs are very big, that's why.
No, that's a great question. So first of all, we have the device if you want it for your kitchen. It's just expensive. So if you have the money, we can give it to you today. But the idea of post-processing and doing the inference and some sort of machine learning, so the inference part we think is going to be manageable on an integratable device. The training is going to be the hard part, and that's the part that we kind of underestimated at the beginning. So the goal is that we can actually integrate the whole thing. So it's not going to be as smart as ChatGPT. It's just going to be a smart to understand a nonlinear photonic device. So in some sense, it's very specific.
All right. Thank you for that excellent talk, Alireza Marandi.
Thank you.
Okay.